Hi everybody, welcome back. Marantz 2240 stereo receiver. These are really nice receivers, and I hope we can get this one up and running well. This belonged to an employee of mine, and it sat in a garage where vehicles were serviced and things. So it is covered with cigarette smoke and exhaust residue and dust and everything that a functioning automotive garage would subject it to. Spent the last 20 years of its life there. Apparently it somewhat works, although I've not tried it yet. And we're going to open it and see if we can get this thing running and get it all restored and bring it back to its former glory. So if that sounds good to you, stay tuned, and that's what we'll be doing. Now, even though this thing looks relatively dirty, I think it's just surface dirt, and I think it'll clean up. There's really no scratches or any really bad things on it. It actually looks to be in pretty good condition. You can see some just some stuff from sitting out in the cold and so forth over the years, but that should all clean up. I don't really see any rust on it as per se, but really the truth, we'll find out the truth when we get this thing apart. So let's get the cover off and look inside. Okay, we have the screws removed, and let me put this cover down. And oh boy, a Shango special. I think this is another Nosferatu habitat. I don't know, I think he may show up in there. But yeah. Yep, mouse feces, dirt and grime. Wow, I didn't expect that. Okay, I will be right back momentarily. Okay, after donning the appropriate paper, because this was dropping turds all over my bench, and getting the nitrile gloves and shooing Mr. Nosferatu out, we can now try this out. I just have an antenna and some speakers connected. I was told that it works, so I still have it on a current limiter, but let's see what we get. Ooh, that didn't sound good. That sounded like I heard a buzzing, but it sounded almost like the relay trying to come in, but not able to come in. Let's try it one more time. I'll move the microphone over. You hear that? Not sure what that was, but I think that was the protect relay deciding that it did not want to come in. So obviously we either have a leaky transistor, we could have a shorted capacitor, we could have a bad contact somewhere. It could be any number of things, but obviously this has a little bit of an issue. Now, since this is not a resurrection video, it's an actual restoration video, I'm going to go with my normal protocol, and that is to clean all this out. I hate troubleshooting things and working on it, with all this crud all over the place. So let me get this at least somewhat cleaned out. Let me change this thing's diaper, because obviously it's full, and I'll be back.
One eternity later.
Boy, you talk about putting the cart before the horse. So it's probably a week or so later than the last clip that I just did. And this thing was just so filthy. And you know me, I don't like working on that. It's so difficult to do anything when you get crud all over everything. So I slowly started taking things apart to clean them, and before you know it, I'd work 20 minutes and then I'd get called out or have to do something. So this is just little bits and pieces, and well, it turned into just stripping the whole thing down and cleaning it before I even got a chance to do much troubleshooting electronically. But I'm truly not worried about the electronics. I know whatever's wrong, I'll be able to fix it. But this is certainly not the way to do a restoration. You typically just kind of brush it out a little bit, and then you test it and find the electronic problems and make sure you can fix them and kind of roughly get it working, and then do your cleaning. But like I said, we're doing placing the cart before the horse, as they say. And it's kind of ridiculous to take it apart to clean it, then put it back together to troubleshoot it. Because this is a restoration and not a repair, I'm probably going to replace some of the critical components before I put it back together. Those boards were terribly dirty. I tried using my typical method of taking the isopropyl alcohol and brushing, and there was so much crud it would just reconstitute it and it would just turn back into crud as soon as it dried. So what we did was I ended up taking the boards and placing them in the ultrasonic cleaner, and look how good it came out. It looks like brand new. Now this is not something I always like to do, because ultrasonic cleaners, at least in my experience, and some of you may have different experiences, but some of these smaller transistors will sometimes be damaged by that. And I don't think it's because of water ingress as much as I think it's because of the high frequency vibrations, the mechanical vibrations of the ultrasonic cleaner. But I don't know. All I know is this one cleaned up really well. We're probably going to recap it. I mean, there's only 4 capacitors. These are those, a couple of these are those orange ones that tend to go leaky. And if you do that, how much extra work is it to do these ones, which these Nippon Chemicons usually don't go bad. They usually stay good, but I'm going to replace them because they're 30, 40 years old or more. I'm just going to replace them. It doesn't cost me anything. I have them, and while it's apart, it's very easy to do. So I'm really happy with that, and I even did the tuning gang and the tuning board, and I'm really impressed with how it came out. It looks really nice. So I'm going to go through the rest of this and finish cleaning it, and you can see to clean the chassis I've just been using some of this goop hand cleaner, and this stuff works better than anything else. I mean, I've tried, you know, alcohol and cleaner, you know, like cleaner degreaser and window cleaner and all of that. None of it seems to work. I have used that what's it called, the Quick Glow, but Quick Glow is kind of expensive, and this stuff so far has been working just as well as that. So I haven't gotten a Quick Glow out yet. If I need it, I'll get it. But you can see once you start working on it, it takes most of this stuff up. Now some of this stuff is really caked on there, and it just won't come off. But I think it'll be good enough that it'll be presentable. And most importantly, I got rid of most of the mouse urine and feces and all that, and it took quite a bit to clean that out. But it cleaned up pretty well. It didn't really ruin the transformer as much as I thought it would. It doesn't look brand new, but it looks presentable. And so yeah, we're just going to keep cleaning. Once I get this cleaned up and I get to doing the boards, I'll come back and I'll show you some of the work on the boards. Let's take a little time in this video to go over some theory and kind of go over some of the reasons why I'm starting to really like this receiver, this particular model. Now, first of all, the 2240, there were a couple different versions of it. There's the 2240, which is the one that we have, that we're working on. And then there's also a model 2240B. And there are some differences. But even beyond that, there are some differences between the 2240s, depending on the build date and so forth. In addition to that, Marantz also made a Model 2238 and a Model 2238B. Now, the 2238 is, of course, rated at 38 watts per channel. The 2240 series, 40 watts per channel. So they're all about the same power. And they were all made within, similar time frame. They were made from around 1974 up to about 1978, 79, somewhere around there. So it was about a 5-year run that they made these 4 receivers. And depending on what year it was when they came out. And some of these models actually overlapped one another. They were made the same year. Now, why do I really like these so much? Well, there's a few reasons. There's a few things that they did. You have to realize that this is a lower powered amplifier. It's kind of a medium power, 40 watt per channel range. And so it's not one of the big monster receivers, 120, 200 watts per channel or so forth. But yet, some of the things they did, some of the attention to detail, shows that this amp can perform just as well as the bigger ones. And so for what this is, this was a great deal, for what you paid for these back then. And even today, it seems like the 2238s are more common and more popular. And you don't see the 2240s as much. But I actually kind of like this particular one right here a little bit better than the others. So let's look at why. So first of all, we have the big picture here. That's what we're looking at. And you have the power supply here on the left. And down here's your protect circuit. You see the relay and so forth, and we looked at that in the actual unit. But up here you have a regulated power supply, which that's not too uncommon, because that feeds the phono section. So that's right here. So it's actually a very quiet, very regulated power supply. But if you look, follow the blue line I highlighted, it goes along here, and this regulated power supply actually also feeds into part of the power amp section. Now we're going to look at an enlarged version of this amplifier section and kind of see what this is all about. This is one of the things that I really like about this amplifier. So now let's look at a little bit zoomed in version. All right, well, didn't have a lot of time to sit at the bench over the last 2 or 3 weeks. So I did have a little more time to sit at the computer in the evening, so I kind of got crazy with some of these schematics and kind of looking over things. And I redrew some of these, and we'll go through it. This is the amplifier in its stock form, or at least my amplifier in its stock form. And you can see this particular unit, the 2240, and it is the only one of the 3. So the 2240, the 2240B, the 2238, and the 2238B. This is the only one that has 2 NPN transistors for the output. This is called a quasi-complementary output. All the other ones will have a true complementary or a complementary symmetry output, meaning that one transistor will be NPN and this bottom one here would be PNP. And this is an older design, but I actually like it. A lot of people say that this isn't as good as a true complementary, but when done properly, it can be every bit as good. So why do I like all this? Well, we'll get into that here in a second. Now, the first thing that I like about this amp is, it has your typical long tail pair or differential input pair, and it has a somewhat kind of regulated here offset adjustment using this stabilizer right here, which H704 I believe is a, what's it say, MV13. And if you notice, what I did up here was in the gray lettering I put some equivalent replacements that you could use for these if these transistors go bad, because these old ones you really can't find some of them anymore, or they're expensive if you do. These are modern ones that you could purchase at Mauser or DigiKey or whomever, you know, wherever. So I just kind of did that. But I like the way this thing is designed, but there's a few improvements that we can make to it. If you notice, they're coming in with the plus 36 DC volt rail. It goes through this 1K resistor, and then if you go here, it is regulated by this 17.3 volt Zener diode. So you have 17.3 volts up here. Now, if we do a little bit of math, the schematic says that at this point, on the other side of this 6.8K resistor, we have 0.7 volts. And if you do the math, 17.3 minus 0.7, you have about a 16.6 volt drop across this resistor. This is important. If it is 6.8K, if you take 16.6 volts divided by 6,800 ohms, okay, so I equals V divided by R, you end up with 2.4 milliamps roughly of tail current on this differential pair. And this kind of acts like your current source up here, but it's not a very good one. We'll get more into this later. Anyway, moving forward, this is one of the things that's kind of unique about this amp. They take the regulated 35 volt supply that comes from that feeds the phono stage, and they also feed the bias circuit. So you see this purple line here? Wherever you see this, this is actually your bias circuit. And your bias adjustment pot is right here, and it's bypassed by this 56 ohm resistor. And then we have this other resistor here with a thermistor, and this is going to be coupled to this driver transistor on the board thermally, so that as this changes in temperature, it's going to affect the resistance of this thermistor here, which is going to adjust the bias accordingly. So it kind of allows the bias to track with the temperature. In addition, you have this stabilizer up here, and it's coupled thermally to the heatsink of the output transistors, and it does the same thing. It's in that same loop with this. If you notice, it's in series with it, and it will also thermally track with the output transistors. So your drivers and your outputs both have thermal tracking in the bias circuit. In addition, something you don't really see on lower powered amplifiers, you have these two transistors right here. These are actually overcurrent limiting transistors. So these are here for the purpose of preventing the output from going into an overcurrent situation. So if you drive this amplifier so hard that into a load that will cause excessive current into these output transistors, these will actually start to clip or clamp off that drive signal to prevent the amp from overdriving into an overcurrent situation. This is not anything uncommon or unique, but it is uncommon in the smaller amplifiers. You normally don't see this type of thing until you get into the bigger 100 watt amps or bigger. Now, a little side note, the realistic STA 2000, it's a 70 watt amp, but it has a lot of this stuff too. It's a similar design to this amplifier, and that's another one that I really love. I think it's a great amp. If we go across here, we were talking about quasi-complementary. So why do people not like it? Well, if you look, here's the driver and here's the output on the positive going half cycle of the amplifier. And if you notice, we're coming out of the emitter and we're going into the base of the output. So come out of the emitter of the driver into the base. So it's an emitter follower circuit, and this is a very typical, what we call a Darlington pair. And one of the things of a Darlington pair is the turn-on voltage is going to be the VBE drop of this transistor and the VBE drop of this transistor combined. So it's going to be approximately 1.2 volts for the turn-on voltage. Now if you look down here, it's a little different. You have a PNP transistor, and the base of this is connected to the collector of the driver. So you have the collector of the driver driving the base of the output. And we call this a Ziclay pair, okay? And it's named after George Ziclay. He was a Hungarian engineer. He lived from about 1909 to about 1998 or so. And he moved to the United States, I think somewhere in around the 1930s or so. He was a brilliant electrical engineer, and this design bears his name because he's the one that actually designed and patented this. And it does have some advantages over the true Darlington. So this is like a complementary Darlington, is another word that people use for it. And if you notice, the values of these resistors are flipped around. So you have, on the collector you have 10 ohms, and on the emitter you have 220 ohms on the NPN side. The PNP side is flipped around because of the polarity. But you can see that the collector is driving the base, and therefore the turn on for the output is only going to be 1 VBE drop of this output transistor. So this one's only going to need about 0.6 volts of drop before it gates and turns on, or begins to conduct. So they're mismatched, and that mismatch in the VBE of these two circuits, the Darlington versus the Ziclay, is something that some may argue makes this an inferior design because it's not symmetrical. But you kind of take care of that in the careful design of the amplifier with the DC offset point and your bias, and the amplifier will actually work outside of that. And there can be an argument that maybe they're a little bit different in their linear regions, but that's kind of, I don't know, kind of grabbing at straws, I think. I don't know. But anyway, when done properly, this can be a very effective and good sounding design. Now, if you go to the model 2240B, I'll show you this. It's a true complementary design, and you can see it has the NPN and the PNP. And you can see in this one, they're both actual Darlington. This is an NPN Darlington pair, and this is a PNP Darlington pair, because in both instances, the emitter of the driver goes to the base of the output. See here? So in theory, they both need the 1.2 volt forward VBE drop to turn this circuit on and get it to conduct. So they match, I guess is what you're saying, is what we're saying. Now, strangely enough, these transistors, the PNP and the NPN, in most cases, they might be complementary design transistors designed to complement one another, but quite often they have very different gain functions too. The HFE is different between the two. Whereas in the older design, you can actually use matched pairs on these because these are identical, the same part number and everything, and you can actually gain match these and get them very accurate. Whereas you can't really do that with these. You can see some other changes they made in the 2240B, and that is anywhere you see the green marker, these are values that they've changed from the original. So if you look here, the old value, for instance, up here you had a 1.8K resistor, but in this one it's 2.2K. And you might get fooled into thinking that the reason some of these values back here were different is because this one is a true complementary and this one is a quasi-complementary, but that's really not the case. These are some improvements that were made in the amplifier, and they will work regardless of how the output is configured. So for instance, they changed across this bias resistor. It's now a 1K resistor. It used to be a 56 ohm. That opens this up and gives it more adjustment. Okay. In addition, they did the same thing here with the bias circuit, with this thermistor. This is now a 1K resistor, whereas it was a 75 ohm resistor. And on ours, they had already made a production run change and changed it from 75 to 100 ohms. So you can see anywhere I put these gray numbers, these are the actual values that my amplifier had. Even though mine's a 2240, it doesn't match the schematic. And this is pretty common. You'll see this a lot in Sansui and in Marantz, where they'll make a production run change right in the middle of production run and to make improvements. So anywhere you see these gray markings, that's what I have on my amplifier when I got it. So you could see this 33K is now a 56K. And on the 2240B, it's an 8.2K. So you can see a lot of differences. The same thing here with the DC offset. You can see they kind of regulate it by clamping the voltage drop on this side with this stabilizer. And they do the same here, but on here, notice they use just a resistor divider network of 22K for the top half of this pot, whereas on this one, they're clamping it down on the other end to two voltage drops and diode drops. So this is very specifically set on this one. So this is a more accurate offset circuit. Again, this has nothing to do with being complementary. So these are some changes between the two, and when you compare them, you can see these are good things. Now, you're going to see on the amplifier boards, when we rebuild them, you're going to see some of these components are not present on the board, but the silk screen and the holes and everything are there on the board. So they were already, you could see on my version that they were already making those changes, but they hadn't quite implemented them yet. So this is all really interesting stuff that we're going to see as we look, rebuilding the amplifier boards. Now, as I was saying, I'm going to make some changes and see what it can do to this amplifier. Again, this is my amplifier, my receiver. I'm going to keep it, and I can always restore it back to its original stock values if I want to. But what fun is that? This is a hobby to me. I'm not rebuilding something to be in a museum for someone. I'm rebuilding it for myself, and I want to see how this will affect things. So I'm going to make a few changes to this original design. I'm going to use some of the ideas that Marantz used in their later 2240B model, and then we're also going to talk about some other changes that we're going to make to this that were not in either one. So let me show you the schematic for that. Okay, here's the updated schematic of what I'm going to propose to try. And what we're going to do is we're going to make this change on one amplifier board only. And then we're going to compare it in performance and do some measurements to see how it compares to the original stock design. And we'll rebuild the stock design too, but we're going to just compare to see if there's any difference, if it makes it better, or if it makes it worse. We'll find out. So the first thing you'll notice is any place you see the red lettering, okay, so here and here and here, down here, right here, all of these, any of this red stuff, these are all changes that we're going to make. Now some of these resistor values, you can see, we changed to match the newer design, okay? And another one that I forgot to mark in here is I did change this to a 1K, this 56 ohm. I did open that up. So I didn't get that on the schematic here that I made. In addition, we're going to add that other stabilizer to the top here, and we're going to make our own stabilizers, and we're going to use some diodes called RL202s, and you'll have to forgive some of the fuzziness of the printout here. I might have a better copy of it. Let me see. Yeah, I do have a better copy here. This one's a little less fuzzy looking. It printed out better. There we go. So we're going to add these, and they're going to be RL202s. We're going to use 2 of them in series, and we're going to take the stabilizer that was down here, this MV13, we're going to replace it with a couple of RL202s. We're going to change this resistor to 4.7K, and we're basically going to make a more solid DC offset, or more stable DC offset adjustment here. We're also going to change this R706 now to 8.2K, which is going to allow a little more current to flow, because now this is going to be what determines the maximum voltage up here at this point. So you have it here at the bottom of the pot and the top of the pot. We have a specific voltage drop of only 2 diode drops. And you can see this all ties in with your global negative feedback circuit. Okay. Now, a couple other things. Most of this is pretty straightforward. You can see, and we explained all that. We're going to add these capacitors here, and we're going to change the value of this one. These are just in there to prevent the amplifier from oscillating, just kind of to prevent that. You don't want these to be too high of a value, or they will start to affect the high frequency response of the amp, but we want it to be high enough capacitance to prevent any type of oscillation. So that's what those were in there for. Okay, so the last thing we're going to look at is this differential input pair here. And this is quite often referred to as a long tail pair. And this is a neat design in that the 2 emitters are tied together, and that's why we call this the tail. And on the collectors, whatever you put in the base, when you drive these, the difference here will show up down here. And that's why it's called a differential pair. Now, there are a couple of disadvantages to the original design, the way you see it here. You have your 17.3 volts feeding this right here. And as you can see, the schematic says that it's 0.7 volts at the emitters. So this kind of acts like a current source. And if you do the math over here, you have about 2.4 milliamps of idle current, okay, if that makes sense. And the problem is when we start turning these transistors on and they begin to conduct, either one of them, the voltage drop is going to change across this resistor, and also the current through this resistor is going to change. And therefore you're going to have varying current between these. And of course, what are transistors? They're current controlled devices. The problem is when the current changes like that on these, especially when these are being driven hard, they will begin to dissipate more power, which will cause heat, which could cause them to drift and can cause everything to go out of balance a little bit. In addition, the excess current can also affect the signal at the output and give you distortion. Now, a carefully designed circuit like this that's working well within its linear region and its operating point, it'll still perform very well. But you just can't drive this thing to its limits, especially if you have like a big peak or something go through there. So what we're going to do, what would be nice would be, instead of having a fixed load here of 6.8 kiloohms, what if we would vary the resistance so that the current would stay the same? Well, such a device exists. It's called a constant current source. And that's what we're doing right here. And this is just a little circuit. I'll show it to you. It's kind of I'll have to zoom out. I don't know if I'll be able to get this whole thing on the... Yeah, I can fit it, I guess. So all it is, it consists of 2 transistors, some diodes that are going to set up a specific voltage drop here, and then these 2 emitter resistors that are going to actually determine, by what resistance we select, what current will be flowing through here. So essentially, just with these few components, you can have a constant current source. So no matter what voltage you put across here, you will always have a constant current. In this case, it's designed for about 2.5 milliamps. So no matter what voltage I put on here, between here and here, there will always be 2 milliamps of current flowing through here. So this is actually an active load, as they call it. And the reason I use this design, because there are single transistor designs that are used in these circuits and so forth, but I'm using this because it's something I already had. I have a whole bunch of these boards printed up, and this is a little constant current source board that's very adaptable. You can change the components and everything on it. This was from another project, but we can populate this with different diodes and different resistors and so forth and get whatever current we want in whatever operating voltage range that we want. So that's what I'm doing. And the nice thing is we can just remove the resistor from here and replace it with the constant current source in its place. Just 2 lead, just plug it right in. Now, there's a downside to all of this. These resistors will now work, these transistors will now work with this constant current source, and this will keep them from really changing how much power they're going to dissipate. But in doing so, you now have a limited amount of current that's going to flow through this tail. So this becomes a current divider circuit, and if you use up, if this dissipates a certain amount of current, then whatever's left will go on the other side. So you can never have more between these two than 2.5 milliamps combined. What that is going to end up doing is, as you introduce those different currents through these resistors, these fixed resistors, you're going to have a similar problem down here. And essentially, in a nutshell, what's going to happen is this is going to have reduced gain. So the gain of this circuit with these fixed loads is going to be different than the gain, is going to actually be higher than the gain of this one with this active load up here. Now there is a way around this. We can take 2 transistors and put them down here in a certain configuration called a current mirror. So what is a current mirror? Well, what a current mirror is, it's also an active load. So it will change the effective resistance between these so that these 2 legs will always have exactly the same current flowing through them, an equal amount of current. So you will always have half of that 2.5 milliamps here and half of the 2.5 milliamps here, no matter how hard each transistor is turned on or not turned on. And what that does is that restores that gain figure. Because remember, we're trying to amplify the voltage. This is the VAS stage, or voltage amplification stage. We don't really care about driving a heavy current because we're not really looking at power. We're just looking at voltage amplitude to drive into this driver circuit. The unfortunate thing is we can't do that on this particular amplifier without really modifying the board a lot. Okay? So we're going to just stick with this, and we're going to have to come up with a way to deal with this reduced gain. Fortunately, the way this thing was designed, we can make a small change to our feedback resistor and restore the amount of gain that we lost. And I'll get into how we do that when we actually do the testing of this module. So pretty interesting stuff. All right, I think we've seen enough of this, and there's a lot more you can talk about with this stage. It's a very important part of an amplifier, and you can really look into this a lot more if you look at Bob Cordell's book, what's it called? I think it's called Designing Audio Power Amplifiers. And another good book I recommend for learning about just this basic theory, if you're just looking for notes, like a reference manual, would be Horowitz's book called The Art of Electronics. Really another good book. Those are two books, if you work on amplifiers, I recommend you should have them. And if you're just basic electronics, Horowitz's book is a must. There's a lot of good books out there, but that's probably one of the best ones you can get, just for general coverage of that. It's not a teaching book, it's a reference book. Think of it as an encyclopedia. You just need to look something up, it's there. Anyway, let's get to the build. Okay, this is where the video is going to get interesting. Hey, they all got to go in a different direction, don't they? Okay, so as you can see, this amplifier on the left has not been touched, has not been modified. It's just been cleaned, that's it. None of the components have been replaced, nothing's been done to it. And this one over here has been pretty heavily modified, as you can see. We'll get into why I did this later on. But I have the amplifier connected to a power supply, and I'm feeding the bias supply and so forth from the main supply, because I actually have a heavily filtered regulated supply, so we can do that. We'll get into that later. And I just want to show you where we are with performance. Okay, we're focused on the scope, and I'm on 10 volts per division. And if I turn this on, I have it set just to barely starting to clip. And you can see it's clipping not totally symmetrically, but very close. You see right there? Right there's a wee little bit of clip there. Nothing there yet. If I go a wee little more, I'll have clipping. And if you read from the center up to the top of the peak, it's approximately 28 volts. And that's 28 volts peak. If you take the RMS value of that, that's going to come out to somewhere around 19.8 volts. And that equates to about 49 watts. And remember, this is a 40 watt amplifier. Okay? Now, here's the more important thing that I'm concerned about. I'm going to take the, let's see here, and I'm only going to feed 2 millivolts now into the amplifier of a signal. And we're going to look at a very, very small signal. I'm now set at, you can see up here, 50 millivolts per division, because I have a times 10 probe. And at 50 millivolts per division, if we turn this on, it's hard to sync with it. It's hard to get the sync to lock in. But you can see I have a tiny little signal, and that's less than 50 millivolts right now. And as you can see, it is perfectly clean. There's no crossover distortion, nothing. It's very, very clean. The bias level, when it's sitting idle, which we'll go back to idle, is supposed to be around 8 millivolts at the test point. And you can see I have it set. It's right around 7 millivolts, so that's good. The amplifier is very cool. It's not even above room temperature at this point in time, and all of the transistors are totally cool. This is the only one right here that even gets above room temperature, and that's good. We'll explain what all we did to this later in the video, but I think what we're going to do is we're going to move all our test gear over to this side, and we're going to try this module out in the same manner and try to compare. I bet you, I don't know if there's going to be much measurable difference right now, but we'll see. Oh, and in case I forget to mention, which I just did, I did have this connected to an 8 ohm dummy load when we were doing those tests just a moment ago. Okay, looking at a 10 kilohertz square wave, you can see we have a little bit of issue with the rise time here, but other than that, it's not bad. It flattens out. If we add some capacitance to it, I'll try 3 different caps, and we're just going to compare to the other amp. So this is a 0.1 microfarad capacitor across the load. And you can see you don't have really bad ringing or anything in there. And that's what we're looking for. Now I'm going to get kind of crazy. We'll put a 1 microfarad capacitor. These are all non-polarized, by the way. And you can see we're getting a little bit there, but it's controlling itself pretty well. And now this is really crazy. A 3.3 microfarad capacitor. And you can see the waveform gets pretty distorted, but we don't break out into oscillation. That's what's important. Okay, now we'll test the other amp that's unmodified. Okay, same setup, same test. Original amplifier. And you can see there's a lot more gain on this one, or at least a little bit more gain if I turn it down. And you can see that looks pretty decent. It looks about the same as the modified one. If we put the 0.1 microfarad capacitor across the load, pretty similar. It rings for a little bit further, but still pretty square, looking pretty good. Go to the 1 microfarad. And you can see now this starts distorting in here, where the other one didn't really do that so much. We'll have to go back and check our footage. And the 3.3 microfarad, pretty bad, but so was the other one. So I would say they function, at least from our preliminary tests, they're very similar to one another. Okay, we're back to a 1 kilohertz sine wave at about 40 watts. And when we look at the distortion figure, not bad. Not bad at all. And that's for something that's sitting on a bench connected up with crocodile clips and jumper leads. Okay, well, before I show you that, here's the unmodified amplifier. It is connected in the same manner, and we're set to the same output. And as you can see, almost the same harmonic distortion figure. So what did I learn from all of this? Well, a couple things. I learned that, number one, you can modify these and get very good performance out of them. But number two, I also found out the performance was adequate to begin with. And although we could probably really keep testing this, put it back into the amplifier, and compare the two modules side by side, we may be able to find some small differences. But really, at the end of the day, is it going to make that big of a difference to how it sounds? I don't know. I just know that I can't measure any difference, and I'm using old capacitors. Basically, everything is untouched. I never even set the bias and DC offset. I left them the way they were. And you see how it performed. So, there you go. Judge it for yourself. Okay, let's see if we can solve this gain problem. So the first thing I want to do is measure the actual gain of the original amplifier as it sits untouched. So I have it all wired up, and I have a pretty precise 100 millivolt RMS signal. So it's 0.1 volts. See there, 99.91 millivolts feeding into the amplifier. And I have an 8 ohm load connected to it, and I'm reading across that 8 ohm load, and I am getting 1.83 volts out. So that indicates a gain of about 18.3. So this will amplify the signal about 18.3 times whatever's going into it. And if we increase to a half a volt or 500 millivolts, you get about 9.3 volts out, which still comes out to about 18.3 gain. So that's our gain of our amplifier. Okay, doing the same test on our new modified amplifier with 100 millivolts input, we're getting about 1.24, 1.243 volts out, which would indicate a gain of 12.4. So the old one has 18.3, the new one has 12.4. The reason for that is the change that I made in the differential pair at the front end of the amplifier. If we look at this, here's your differential pair. You have 17.3 volts fed in here because you're coming on your DC rail through this resistor, and then it goes across this Zener diode, which clamps it at 17.3 volts. This acts as your quote-unquote current source, this 6.8K resistor. And this can actually change and cause the current in this circuit to change with it. Now that can cause distortion, although in actuality, as you saw on our test, it really didn't because of the operating parameters that they chose for this circuit. But by putting a constant current source in here, which is what this little module does, we're eliminating that, and it is actually changing the gain of this little circuit. So that's going to be affected by our feedback. So this feedback resistor is probably no longer valid for this setup, so we will have to modify this a little bit. We will actually have to increase this resistor a little bit. So let me go through and do a little bit of testing, and we'll come right back. Okay, as you can see, I removed that 33K resistor, which was right here, and I replaced it with a 51K resistor. So that's this one right here. Okay, this is your feedback. All right, let's see. If you remember, 0.1 volts in was giving us 18.3 volts out in the original amplifier design. So let's see what we get now. I have 0.1 volts going into the amplifier. How about that? Pretty close, huh? All right, how did I figure out what value of resistor to use? Well, of course you could just randomly replace resistors, right? But I used a little trick. I don't know if it works every single time, but I've used this before and it has. So what you do is, let's take a look here. It's all crooked here, but hey, that's what you get. Let me turn the amp back off. So if you recall, we had a gain of 18.3 on the original design and a gain of 12.4 on the new design, on our redesign. And if we take 12.4 divided by 18.3, you get about a 67 or 68% difference. Okay, so this is about 68% more than this. So what I did was I took that 68% and I times it. So I took 1.675, let's say, right? Or 677, 1.6775. And I times that by the 33K, and I came up with 55K. All right, 55.35K. All right. So there's two different resistors. There's a that are standard values. There's a 56K and a 51K, and I chose the 51K to be a little bit on the safe side. And this is always going to give you just an approximation. There are other factors that will come in that will affect it. But first try, that brought it right in where we wanted it to be. So anyway, it's working now, the whole amplifier. And what I may do at this point is I might go through and do another gain analysis to make sure that it works all the way across the frequency spectrum. So I'm going to connect the frequency analysis unit, module up with the MDO 2204 and just make sure that everything is still good. Okay, I hope the contrast isn't swamping out the camera. Let's run the analysis now and see what we get. I can tell you already it's right on. Hopefully it'll hold out all the way to 20 kilohertz. Look how flat that is. Nice. Very nice. So let's scale the Bodhi plot. And there you have it. Very good. Very, very good. So I'm totally happy with it. So now we did all this work and all this mathematical analysis and all this stuff and all this experimentation, and we ended up having two modules that pretty much still perform the same as one another. So was this worth it? That's the question. And I believe really what it comes down to is stability under difficult loads. All of those sorts of things are going to have to depend on listening to it in the real world with an actual speaker load on it. The problem is everything that we do on this bench, with the exception of the little square wave test with the capacitors, is a totally DC resistive load that we're testing on. And it's very difficult to see how the amplifier is going to react to difficult loads that present a reactive load to the circuit. So whether it be capacitive inductance or capacitive reactance or inductive reactance, boy, I'm getting tongue twisted here. But those different types of reactance can affect things differently. Will it make a big difference? Don't know until we try it. All I do know is that we did an awful lot of work for what doesn't seem to be much gain right now. Now I will argue, because of the coupling we did on the transistors and a few things like that, the amp will be more stable, especially through different temperature changes as the amp heats up and things like that. We really haven't tested that. But with the exception of that, I think this is a really well performing and well designed amp. The people that design these things know what they're doing. And as we saw, they made changes over the life of this thing. This is still, remember, as we saw earlier, this is still a model 2240. It is not a 2240B. But if you notice, these amp modules have some of the mods that are seen in the 2240B and some that are not on the 2240B. So this amp was a late production of the 2240. And you can tell by even having, some of the positions are not occupied, but they're already there for some of the added components, that this was a very late production just before the 2240B came out. Very interesting. So some of these things have already been done on this one that were not done on the earlier versions of the 2240s. All right, we have two choices here. We're ready to reassemble the amplifier and finish up the receiver. But we either have to restore the amp that we did all the work to it back to stock, okay, using new components, of course, or we have to do the upgrade to this one the same as the other one we did. 6 of one, half dozen of the other. Now, the way I look at it is this one, we're still going to have to take it apart to recap it and so forth. And the other one is completely done, so it doesn't need taken apart. So what I'm going to do is I'm going to modify this one to be the same as the other one. And again, our tests are inconclusive as to which one is better or if they are any different than one another, but all I know is that I did the one, it's finished, so I'll do this one the same way, and we'll test it, make sure it's good, and that'll give you an opportunity to see what changes I make to this board. So if that sounds interesting, stay tuned. Okay, I've gone through the schematic, and in blue pen are all the things that we're going to actually change. What we're going to do first is we're going to replace this 100 picofarad with a 220. We're going to add a second 220 down here, and we're going to add this capacitor right here. Now what these are supposed to do is they prevent oscillation and make the amp a little more stable, especially at high frequencies or at difficult loads and things like that. You can see they were already on that route with this board, because this capacitor here, 707 is already, I'm sorry, 711 is the one we want to replace. Where is it? 711 right here. And then they also cut the holes for 713 and for 712 right here. See there? So we don't really have to do anything except for install the capacitors. So I have a couple of 220s, and they're just plain old ceramic caps. They don't have to be high accuracy. They don't have to be NP0s or anything like that. And then this capacitor right here is 0.002, and we're going to install that, which is this one right here. So I'll put those in. I'll be right back. Okay, our three little capacitors are replaced. We have the one here, and then this 0.002 here. Next, we're going to replace this 100 ohm. Remember from earlier in the video, this is a 56 ohm is what it was called for. There's actually 100 in there right now. That's how this one came. The other one was like that as well. And we're going to replace it with a 1K. What that's going to do is that's going to kind of open this control up and allow you to have more adjustment on the bias setting. We're also going to increase this from a 75 ohm to a 1K, which is going to allow this to have more influence over the bias circuit as well. So it should have a little bit better thermal tracking. So let me get those two resistors replaced, and then we'll be back. Okay, we have the two resistors replaced, and if you notice, they are physically smaller. If you look at the original right here, and then you look at the new one. But the funny thing is, when you look at the schematics, or I mean the parts breakdown, you can see all of these resistors are actually 1/4 watt resistors. So these two resistors we just replaced are 1/4 watt. These resistors, believe it or not, this one and this one, are 1 watt resistors. Now compare that in size to a carbon comp 1 watt resistor. There's a big size difference there, you see. And how can that be? Well, what that means is that each of these resistors can dissipate 1 watt of heat. However, these resistors will flash over at a much lower voltage than these. So if you're working with tube gear, you're better off with something like this, or with a larger carbon film resistor or something, because even though these can handle a lot of heat, they can't handle a lot of voltage. And that's why these are smaller. But because this is a low voltage solid state circuit, this is perfect for in here. So that's why they look different. Now the next thing we're going to work on is the bias circuit, or I'm sorry, the DC offset circuit. So if you look in here, you got to kind of follow the path a little bit here, but we go through this 1K resistor, and this comes off of our 36 volt plus 36 volt rail. After it goes through this 1K resistor, it goes across this Zener diode, and this limits current up here, by the way. This Zener diode is a 17.3 volt Zener, so that means at this point you're going to have 17.3 volts. Now that goes two directions. First of all, it goes down and it feeds the differential pair. It also goes down and feeds what's going to be your DC offset adjustment. What they're doing is they have a 33K, which is actually a 56K. They made this change without annotating it in the book or in the schematic. But either way, you have this high resistance resistor right here, goes down to this 22K resistor, and then that goes to ground. So it's a voltage divider. It's picking off of this junction of the voltage divider, and it goes into the top of the DC offset potentiometer. And then the other end of that finds the negative power supply. So here's your minus 36 volts. Goes through a 15K resistor, which actually is a 4.7K. It was a mod that was made. That's what's in there right now. So if we look, we don't have 33K and 15K, but instead we have this 4.7K right here and this 56K right here, and that's factory, you can see. Anyway, they put this diode, this little diode pack, which is this little guy right here. It's 2 diode drops. It's a stabistor. It's very, very stable under different currents and so forth. Very predictable and linear. And it raises this right here and holds it at about 1.3 volts above ground. Negative 1.3 volts, I should say, right here. Up here, they just have another voltage divider, which again can change. So the later iteration of this, they added a second stabistor in place of this 22K. They reduced this to 8.2K. I'm going to do the same thing, and that's going to make this circuit a lot more stable. Now, once we do that, DC offset is not going to be, we're not going to be able to adjust it properly. So we have to change this 1.8K resistor out for a 2.7K. So we're going to replace this resistor, which is already 4.7K. We'll leave that one as is. We'll change this 1.8K into a 2.7, and then we'll remove our 711 and put another one of these diode modules in here. And we have to be careful which direction we put this. Now, the other thing is what diodes we use. That's very important. You can't just take any diode like a 1N4148 or whatever. You have to get something that will track in a similar manner to those little diode packs if you don't have those particular ones. And I want them to be all the same. So what I'm using is these little, well, not little, but these are 100 volt 1.5 amp rectifier diodes. They're not anything special. They're not fast recovery. They're just plain old diodes, and they are a type RL202. There's a specific reason I'm using that particular diode, and that is because they actually are very similar in characteristics to that little stabistor right here. Albeit they will handle a lot more voltage and a lot more current, which we don't need. It doesn't matter. All we care about is that the voltage drop and as the forward current goes through it, how it tracks is similar. And these seem to work really well for these. So that's what we're going to do. We're going to put 2 of them in series and then fit them in place of here and fit that one in place of the R711, which, where did I put that? R711 is right up here. And you can see it's in there. It's right now it's a 22K. Okay, the resistors have been replaced, and R712, which we were going to change out for a 1.8K is already a 1.8K, even though the schematics are still calling it a 2.2K. See it right up there? So again, like I said, this is a late model and some of these values have already been changed. Same thing with this 4.7K. That's already 4.7K. I fitted the little diode arrays here, one here, and I replaced the original one with this so that they match, although they're pretty close anyway. Now we're getting into the differential stage here, and that'll be our last modification. The first thing I want to do is replace these two transistors with a thermally coupled pair. So what I did was I took a set of matched KSA 992s, and let's see if I can find where I put them, and I just put the tiniest dab of super glue on the face of one of them, and I face glued them together, and then covered them with a piece of heat shrink like so, and you have this little bug. And I bent the leads down so you have the emitters in the middle, the collectors, and then the base is on the outside. And we're going to remove these two transistors here and put our thermally coupled pair in there, and they are matched, so that should give us the best performance on that. We're also going to change the input resistor to 3K, and then we're going to install our constant current source. So let's take a look at that. So here's the constant current source that I'm going to use, and I have a whole bunch of these boards that I made up a long time ago for another project. Actually, the components that originally go on here are for much higher voltage, because this was for a vacuum tube project, and it was a current source for a vacuum tube project that had to be 300 to 350 volts. We don't need that for this, so I retrofitted the board with just a, what is this, a KSA 992 and a KSC 1845. And then I used a set of UF 1004 diodes, and then these are, the resistors are 330 ohm, and then the 1 meg in the middle. Okay, when the transistors are installed, it looks something like this. Fits in there real nice. Now, this capacitor here is right below where we're going to mount our current source. And you have to make sure this is polarized, so you want the plus side of the current source to go on the left and the minus side on the right, like that. And it just so happens this worked out that it fits that way. But I don't want the bottom of the board to come in contact with the capacitor, even though the top of the can isn't really physically tied to the cap itself. So I put this little piece of heat shrink, and I left the opening open there so that if the cap does need to vent, it can. And we're just going to put this right in here, like so, if I can do so on the camera while we're looking. All right. And then we're just going to go ahead and get that mounted up, and I'll be right back. Okay, the board is finished, and I just did a quick cleanup with some alcohol. It turned out really nice. And there's our current source mounted on there. It looks just like part of the unit. Well, there she is, all together and looking good. You know, cleaning this took more than anything else, believe it or not, although the video doesn't show it, but it turned out really nice. And the amp sounds really good. It has a really clean sound, really tight bass, and well, we'll do a few final tests on it so you can see. And I'm going to put the top on it and call this one done. Okay, let's try this out and we'll see if my new camera mount works. I have a little arm that I can attach to my new camera mount to mount my Zoom H4n Pro microphone. We'll just try that, and I just want to see how this works. Cue up some YouTube safe music and cue up the recorder, and then I will kind of overlay that when I edit the video in place of the lapel mic sound, and we'll see. So here we go. Start the microphone. Well, I guess we get it. Yeah, this thing sounds good. I'll tell you, the bass is so tight on this amp. It's unbelievable. It turned out really nice. This seems to be the video that just doesn't want to end. I've been working on it for well over a month, and I don't even know what all kinds of things I recorded and didn't record. So whatever bits and pieces I have on this card, I guess that's what's going to be your video. It turned out beautiful. I like the way this thing looks with I replaced the LEDs in it. It had a bunch of the little bulbs for the indicators that were burned out. I don't know if you could see them there. Those are all fixed. I did a kind of a quick alignment on the tuner, and I did not film that because you've seen me do so many tuners and I have so much footage already of this receiver. I didn't get a whole lot of the cleaning process again because I would just come down here and I had a little bit of time, you know, and just do a little bit and then, you know, go back upstairs. So I didn't get a lot of things recorded for that part, but you can see it cleaned up very well. The input jacks for the front tape in and out are broken, and this is something I see quite often on a lot of the other Marantz receivers from this era, and I think it has to do with the plastic just gets brittle and they break, and they're not a normal connector that are easy to find. So I decided not to mess with them. I'm just going to leave it alone. The amplifier modules are all working, and I want to try this out and do our final tests with this all put together to see how it finally performs. I think we're not going to see a big difference with the types of tests that we do from the stock design, but I think our ears, or at least my ears will hopefully be able to hear a difference. I have been playing some music through it, and this does sound very good. I'm, you know, as far as the, you know, just how the clarity. The one thing I can repeatedly say about this receiver in particular, this one now after it's done, is it has a very tight bass sound to it. You know, Marantz is known as, you know, for like very warm sounding bass, and this is still that type of thing, but it just sounds like the amplifier has a little better control of the speakers. I don't know if because you can only explain in words what you're hearing. You can't really portray it through a YouTube you know, video and your speakers and whatever you're listening to, but you'll have to take my word on that it's pretty good. So let's go through and do a couple basic final tests to just see what we have. I have the signal generator set to 1 kilohertz, and let me zoom in on the scope a little bit here, and you can see down here this is going to display the wattage of channel 1, wattage of channel 2, and then of course the RMS voltage for the 2 channels, and then you'll see the wattage bar come up as this thing drives. So let's take a look and see where we get clipping. And I really like this scope. So right there's your clipping point, and if I go just a little bit below that, you can see it's pretty clearly giving us about 52 watts per channel, 51 watts, something like that. Okay, they're a little bit, and the balance control is a little, you know, on this one these use those sliders, and they're not perfect as they get older, but it's pretty close. So for a 40 watt receiver, you have lots of headroom, you can see. If we run it at a reasonable power of, you know, 30 watts per channel, and we go over to the distortion meter, I hope I have it, at that 0.01, I mean, that's very, very low. A little bit of that distortion is just because of the equipment itself. So realistically, very, very low distortion. So that's good. I'm happy with it. And you can hear it. I mean, it sounds really, really good. So that test is good. I'm not going to go through all the things we did on the bench with the amps sitting on the bench. This is a little heftier power supply than I was driving it on the bench with. The power supply on the bench only goes up to a maximum of, I believe, 30, what is it? 31 volts is all you can get out of that maximum, but realistically 30 volts. This receiver, the power supply in this goes up to 36, so obviously we're going to get a little more performance out of it. So let's go off of this now. Let's go up to our MDO 2204, and let's do the frequency analysis. Okay, running the frequency analysis. And we can see right now that just like the 2325 Marantz that we did not too long ago, the signal is inverted. So it inverts the signal 180 degrees. And I explained this on the 2325. What you're seeing is the phase relationship of input versus output, and how it calculates the actual, if it's plus or minus. Once one crosses over the other, it makes it flip again. Don't worry about this. This is inaccurate. What you're seeing up here is the waveform, and you can see that it is inverting the signal 180 degrees between the input and the output. And it seems like this is something that Marantz does on purpose. I thought that it may have had to do with something with the that integrated circuit in the tone amp on the 2325, but the 2240 does not have that. And it literally, the design of the tone amplifier, or the tone control stage of these amplifiers inverts the signals very deliberately. So I don't know if somebody out there knows why Marantz designs their receivers to invert the signal 180 degrees. Let me know. I'm curious. Is there an advantage to it? I don't know. Anyway, you can see it's pretty flat. We're within 1 dB across the board. A little bit of a hump, just a little bit in the mid-range area. That's it. But other than that, it's very, very flat. So that looks good. I'm very pleased with that. So this receiver is working pretty much as good as it can. Now, what have we learned from all of this? Well, a couple things. Number one, we've learned that Marantz really knew what they were doing when they designed these receivers. Because as we saw, we saw it with our own two eyes. We tested it with test equipment. The original factory design of this performed extraordinarily well. And when we did some of the upgrades that Marantz did on the 2240B, and we also on the input stage, the differential pair, we added our constant current source. It didn't really make anything testably different. In other words, we weren't able to pick it up without doing some exotic tests. Now, I think if perhaps we could have done some two-tone tests for intermodulation, distortion, and things like that, but I don't even know if those would have made a big difference. I do think, just from listening to the amplifier, I do think it works really well as it is right now. It does have a little different sound signature to what I'm used to hearing Marantz receivers like this. As far as bass, it's very tight sounding. I do believe that the current source improved that somewhat, and I think that doesn't surprise me, because it's that dynamic sound that you're going to notice the difference on. Am I grabbing at straws and just trying to make excuses? No. This is something you would have to listen to for yourself and judge for yourself. I'll leave that open-ended to all of you. But it was a fun project and a fun experiment, and that's really what this was all about. This receiver was in pretty bad shape when it came in here, and it's one that I'm going to keep now and probably use on this bench, as a test receiver. It's very bulletproof. One of the things I like about it is it's designed that it's really going to be hard to overload this amplifier. It runs extremely cool. This thing sat here running at 30 watts per channel while I was testing it for 10-15 minutes, and the heat sink's barely even warmed up. That's incredible. You never see that. And the fact that this has, even though it's only one of their smaller amps, 40 watts per channel, it has some of the features of the higher end amplifiers, like the overcurrent protection. It has a really good protect circuit, which I did replace the relay, by the way. I put a new protect relay in it. That kind of stuff didn't make it into the video. I didn't record it, unfortunately. So this is a good amp to use, for testing different kinds of speakers, different kinds of inputs. If this amp gets overdriven by something, it's going to be safe. You're not going to really hurt it. And it sounds incredible. So there you go. That's my assessment. And we're going to get this off the bench, and we're going to get a vacuum tube project on the bench next. And this has been over a month goofing around with it. So it'll be nice to finish this up. So until then, I wish you all peace, joy, happiness, and good health in your lives. I thank you for being patient, waiting for this video to come out. And I don't know, if it's going to be something you guys are going to like or not, but I hope you do. Anyway, take care and stay well, and we'll see you again real soon. Bye-bye.